Welcome back. In the previous video, I showed us how to calculate number of electron pairs in a compound. If you'd remember, I gave us a simple formula where I said number of electron pairs, let's just write that as NEP, is equal to the number of valence electrons around the central atom, and then we said you add that to the number of monovalents, and then you divide the sum of those by 2. So number of electrons around the central atom plus number of monovalents divided by 2. But we said in a case where there are charges, maybe you have a charge of -2 or +1 as the case may be, that for negative charges we should add whatever value, the magnitude of the charge, and then for positive charges we should subtract. And we showed how that applied in the previous video or in the previous session before the break. But back to this now. After calculating number of electron pairs and obtaining a result, what does the result usually tell us? The result we get from this calculation usually tells us what we call the electron geometry. It tells us what we call electron geometry of a compound, and usually electron geometry is otherwise simply called geometry. So that when we do this calculation and we obtain a result of, let's say, 2 from that calculation for a compound, we say that the meaning of this is that the electron geometry of the compound is linear. And of course, this linear geometry, you know, we already said from the previous video that from the result you can tell the type of hybridization, where we said for 2 you have sp, for 3 you have sp2, and so on. Now we are saying that the geometry of this sp hybrid would be linear, the electron geometry actually. And then when you get a result of 3, which is an sp2 hybrid, the geometry there would be trigonal. So what I'm giving us now is a list of possible results from this calculation and what kind of hybridization that will lead to, as well as the kind of electron geometry that the compound would have. So for a compound, if I do this calculation and I get a result of 4, I would say that the central atom in that compound is sp3 hybridized, and I will say that the geometry of that compound is tetrahedral. So that's the geometry that goes with an sp3 hybrid. Then when I get a result of 5 or of 6 or of 7, I would say that the geometry, or first the type of hybridization, sp3d, this is sp3d2, and then I have sp3d3. The geometry here for the 5 case is trigonal bipyramidal. Trigonal bipyramidal. That's the geometry for a compound whose central atom has 5 electron pairs. Sorry, for a compound that has 5 electron pairs and whose central atom is sp3d hybridized. Then, if a compound has 6 electron pairs, it means that its central atom will be sp3d2 hybridized, and that means the electron geometry of the compound would be octahedral. And then finally, for a compound that has 7 electron pairs, the central atom will be sp3d3 hybridized, and the geometry of that compound will be pentagonal bipyramidal. Pentagonal bipyramidal. So what I've done so far is interpret the result of this calculation. And in effect, I've said that this calculation would usually give you results between 2 and 7. And for each of those results, you can tell the kind of hybrid that is existent in the central atom, sp all the way to sp3d3. And depending on the kind of hybrid in the central atom, you will know the electron geometry, or simply geometry, of the compound. However, there's a second kind of geometry that we talk about under this. We refer to it as molecular geometry. Now, for molecular geometry, to avoid confusion, we usually would just refer to it as shape. So that's why at some point I said geometry versus shape. So geometry, even though we have molecular and electron geometry, we take the term geometry to refer to electron geometry. Whereas when we're talking about molecular geometry, it is more conventional to just say the shape. Now, I'll tell you that the shape of a molecule is not necessarily the same as its geometry. Or in other words, the molecular geometry of a compound is not necessarily the same as its electron geometry. The only time they can be the same is when the compound does not contain any lone pairs. So if there are no lone pairs in a compound, yes, the molecular geometry and the electron geometry would be essentially the same. However, if there are lone pairs, then the lone pairs have a way of distorting the geometry so that what we get as molecular geometry is no longer the same as the electron geometry. Now take a look at these three guys. That is methane, this is ammonia, and here is water. One thing they all have in common is they have the same number of electron pairs. If you use this formula for methane, CH4, you know central atom is carbon. How many electrons are around it? 4. Plus number of monovalents attached, 4. 4 plus 4, 8. Divided by 2, 4. 4 means what now? sp3. So it means that this carbon is sp3 hybridized. And it means that the geometry of that compound is tetrahedral. If you do the same calculations for these two guys, you'd see that nitrogen here is sp3 hybridized, while the oxygen is also sp3 hybridized, and that means these two are also tetrahedral. However, in methane, you see that all the 4 electron pairs are bond pairs. None of them is a lone pair. Whereas in ammonia, 3 of them are bond pairs 3, and then 1 of them is a lone pair. In water, there are 2 bond pairs and 2 lone pairs. Now, the presence of these lone pairs distorts the shape or makes the shape different from the geometry, in that lone pairs usually exhibit what we refer to as repulsion. So lone pairs repel, even bond pairs repel. So we have lone pair to lone pair repulsions, which are stronger than lone pair to bond pair repulsions, and then the weakest of them will be bond pair to bond pair repulsions. So it's more like in this case, since they are all bond pairs, the repulsions are the same everywhere, so that on the net, on the overall, there appears to be no repulsion here and no distortion of geometry. So that for this compound, methane, the electron geometry is tetrahedral based on this result, and the shape is still tetrahedral. Why? No lone pairs. So when there are no lone pairs, the electron geometry and molecular geometry would be essentially the same. But for these two guys that have lone pairs, their shapes or molecular geometry will not be the same as their electron geometry. So what would be their shapes? In the case of the ammonia molecule, I'm going to give you a simple table after now that you can memorize, so that for compounds of any sort, when you take their number of electron pairs and you consider their structures, you'll be able to tell both the electron geometry and the molecular geometry very easily. I'll show you that very soon. But for now, in the case of ammonia, that it has 4 electron pairs makes the electron geometry tetrahedral. But that there is a lone pair, just one lone pair, will make the shape what we call trigonal. Now, trigonal is of 2 types. There's trigonal planar and there's trigonal pyramidal. What we have here is trigonal pyramidal, not trigonal planar. Trigonal planar is the shape we see in a case where we have 3 electron pairs, and out of these 3 electron pairs, all 3 of them are bond pairs, and then there's no lone pair. That's called trigonal planar. But for trigonal pyramidal, what we have is 3 bond pairs and 1 lone pair, and that's the case of ammonia. Then for water, water has 2 bond pairs and 2 lone pairs. The electron geometry based on 4 electron pairs is still tetrahedral, but the molecular geometry or shape for water will be referred to as bent or V-shaped or angular. So in our books, we commonly see this. They say water has an angular shape, water is V-shaped, water has a bent shape, or water is a bent molecule. Any of those will apply, and we use that term for cases where we have 2 bond pairs, 2 lone pairs. So what I'm going to do now is show you a simple table. What this table helps you do is determine easily what the geometry as well as the shape of a molecule would be based on your results. And I'll use the table. I'll try to make this practical by using the table so that we do not have any issues. So on this first column, I have number of electron pairs, and then on this side, I would have the type of hybridization that follows that. And then beyond the type of hybridization, I need to tell you the geometry. So this will be geometry. Then beyond geometry, I'll have number of bond pairs and number of lone pairs. So this is bond pair and that's lone pair. And then finally, the shape. Yeah, so this is it. That's how a table would be. If I'll advise you, you could pause this video and draw this table out so that you have a copy of it. At any point, you can refer to this table, and I tell you it's reliable, it works. So see what we have. For number of electron pairs, that is your calculation we did earlier. If you get a result of 2, you would conclude that the hybridization in the central atom of that compound is sp. Then you say the geometry of the compound is linear. And usually when there are 2 electron pairs, they would be bond pairs so that we have no lone pairs. And what do you expect for the shape now? The same with the geometry, so we say linear. So that settles that one. So that's for a case where you have 2 electron pairs. But when you have 3 electron pairs, the hybridization there is sp2. And for such cases, your geometry is definitely going to be trigonal. So these ones are constant. 3 electron pairs from your calculation, sp2, no stories. And then geometry is definitely going to be trigonal. But 3 electron pairs may end up being 2 bond pairs and 1 lone pair. Or, sorry, let's start with the maximum. So 3 bond pairs and no lone pair, or 2 bond pairs, 1 lone pair. So where you have 3, that's all 3 electron pairs are bond pairs, no lone pairs, you say that the shape is also trigonal. So this is trigonal, that's trigonal. But we usually add planar to this, so trigonal planar. And then when you have 2 bond pairs and 1 lone pair, the result is a shape that is bent or angular. I'm sure you remember the third thing you can put there, V-shaped, like we said for water. So that's when you get a result of 3. What if you get a result of 4? We've started that already. We said when you get a result of 4, it means that the hybridization in the central atom is sp3. And it further means that the geometry of the compound will be 4, tetrahedral. Tetrahedral. But how would these 4 electron pairs be distributed? It's possible that we have all of them as bond pairs, no lone pair. We may have 3 bond pairs, 1 lone pair. We may have 2 bond pairs, 2 lone pairs. We may even have 1 bond pair and 3 lone pairs. So in that case, we're going to have 4, 0, that's tetrahedral again because there are no bond pairs. And then the 3, 1 case we already saw as trigonal pyramidal. Trigonal pyramidal. And then we said this one is bent, angular V-shaped. But this last one is usually linear. So for a compound that has 1 bond pair, 3 lone pairs, the shape would be linear. So that's for 4 now. So the next thing we are going to write is 5. What if our result is 5? It means that the central atom in that compound is sp3d hybridized. And the geometry in that case would be trigonal, this is trigonal bipyramidal, trigonal bipyramidal. So if we say that the central atom in the compound is sp3d, then it means that the shape of that compound, the geometry of that compound will be trigonal bipyramidal. But what about the distribution of bond pairs and lone pairs? We can have a 5-0 situation, we can have a 4-1 situation, we can have 3-2, and then we can have 2-3. When we have 5-0, what do you expect? Of course, trigonal bipyramidal. So I'll leave that way. So trigonal bipyramidal, that's when there are all bond pairs 5 and then no lone pair. But if you have 4 bond pairs and 1 lone pair, the shape is referred to as a seesaw shape. Some refer to that as irregular tetrahedral. So there's a seesaw shape there. And then beyond the seesaw, for 3:2 cases, we have what we refer to as the T shape. And then for the 2:3, we have what we call linear. Yeah, so that one is linear. So when we have 2 bond pairs and 3 lone pairs in a compound, the shape becomes linear. Now beyond that, the next one I'm going to show us is a case where we have 6 as our result. 6. When the result is 6, the hybrid the hybridization in the central atom will be sp3d2, and the geometry of that compound will be octahedral. Then, beyond the octahedral geometry, what about distribution of bond pairs and lone pairs? Of course, we can have 6-0. I'm sure you are guessing what will be here already. Then we can have 5 and 1, and then we can have 5 and 2. 4 and 2. 4 and 2. When you have 6-0, of course, the shape is still octahedral. Then when you have 5 and 1, we say the shape is square pyramidal. So the SQ there is squared. And then this next one is square planar. So for the 6 electron pair situation, we have 3 possibilities: 6-0, 5-1, and 4-2. Remember, those numbers tell you the ratio of bond pairs to lone pairs. So the last situation we have here, I'm glad this board is able to contain all at once, is sp3d3. When you have an sp3d3 hybrid, the geometry that goes with it is pentagonal bipyramidal. I think we mentioned this earlier. So pentagonal bipyramidal, and usually bond pair to lone pair, what we have here is 7-0, and the shape, of course you are correct, it's still pentagonal bipyramidal. So what I'll do finally, having given you this table, would be to solve 1 or 2, bring out some compounds and show you their geometry and shapes. I'd like to work it out while you watch, while you listen. So for now, you may pause the video and try to transfer this table to paper so that you can try to memorize it after now. Alright, having taken down the table, let me bring out a few compounds and then show you how to get their geometry as well as their shape. Consider a first example, SO3. Let's work with this one first. For SO3 as a case, if you were to find out its geometry and shape, step 1 would be to calculate the number of electron pairs. So number of electron pairs equals, sulfur is surrounded by 6 electrons. So I'm going to write 6 plus, oxygen is divalent. So I can't write any value here, and I'll leave that as 0. When you add those two and divide by 2, you get 3. So having obtained 3, according to the table, we say that the type of hybridization in sulfur here is sp2. Now, what about the bond pair to lone pair ratio? Because if you check your table, you'll see that a result of 3 can be 3 bond pairs, no lone pair, or 2 bond pairs, 1 lone pair. So how do I know number of bond pairs and number of lone pairs? Here we are. The total number of electron pairs is 3. The number you have down here is already the number of bond pairs. That number you are seeing there. So even if I write a compound like CH4, that 4 is the number of bond pairs. NH3, the 3 is the number of bond pairs. Alright? So in this case, the number of bond pairs is 3. And the total number of electron pairs is also 3. So it means that there are no lone pairs. So because I have bond pairs from here, 3, lone pairs, this minus that, 0. It means that the geometry would be what now? Sorry, from here we would have gotten geometry already. From the hybridization of sp2, the geometry is already trigonal, that's settled. But what bond pair and lone pair ratio would tell us is the shape. So that the shape here will also be trigonal. So the shape is trigonal just as the geometry is trigonal, and that's because there are no lone pairs. Come to this next example, ammonia. The same ammonia we saw earlier. Now for ammonia, the number of electron pairs equals nitrogen has 5 electrons around plus 3 monovalents attached divided by 2. So 8 divided by 2 gives me 4. This 4 will lead me to the following. First, hybridization type, sp3. Second, geometry. Because there are 4 electron pairs and an sp3 hybrid, the geometry would be tetrahedral. That's settled. Finally, the shape. To get the shape, I will now write the number of bond pairs, which is this number here. So number of bond pairs is 3. The number of lone pairs, we said it is the result minus this number, because this result tells you that there are a total of 4 electron pairs, and out of this total of 4 electron pairs, 3 are bond pairs here. So it means that the last one is a lone pair. So number of lone pairs, 1. If you check your table, 3 bond pairs, 1 lone pair. The result there is trigonal pyramidal. So we say the shape of the ammonia molecule is trigonal pyramidal. Let's see a more complicated case. Let's look at something like SF4. SF4. For SF4, sulfur has how many electrons around itself? 6. And then the fluorines, univalent, are how many? 4. So 6 plus 4 is 10. Divide 2, that gives us 5. So for a result of 5, I would draw the following conclusions. First, the hybridization in the sulfur atom would be sp3d. That's what a result of 5 tells me. Then, what would be the geometry of SF4? Well, for a result of 5, the geometry is always trigonal bipyramidal. But here comes the main work now. What will be the shape? So to know the shape, I'll need to work out number of bond pairs and number of lone pairs in that total number of electron pairs, which is 5. So number of bond pairs, how do I get that? It is right there looking at me, so that's 4. The number of lone pairs, since total electron pairs are 5, and then we have 4 bond pairs, 5 minus 4, we have 1 lone pair. Now from your table, I think that part of the table is still available, 4:1, the shape of this molecule will be described as seesaw. That's the shape, seesaw. So that's the seesaw shape. So to get the shape, you need to compare number of bond pairs and number of lone pairs. And that's the main reason I gave us that table. I'll do 2 more. And beyond those 2, I'll say bye-bye to hybridization, hoping that you would go and deal with many more cases as you encounter them. So see this next one. See this next one. Let's say we use ICl3. Let's say we also add, let's add 2 more, XeF4 and then HF. Beautiful. So let's work with those 3 very quickly. For ICl3, iodine has 7 electrons around it plus 3 univalents, that's 10, divide 2, that gives us 5. So what's the hybridization in ICl3 in the iodine precisely? We say it is sp3d. What's the geometry? Of course, it follows as trigonal bipyramidal. But what is the shape? For the shape now, I need to know number of bond pairs. So bond pairs equals 3, and then lone pairs equals 5 minus 3, that's 2. So 3:2 is right here on the board. We'll say it has, let me write it down here, a T shape. So ICl3 is a T-shaped molecule. If you try to do the same for ICl5, you get a different result, but that's your assignment, not mine to do. Then for XeF4, xenon tetrafluoride, xenon, a noble gas, has 8 electrons around itself, plus 4, that gives us 12, divide 2, that gives us 6. So based on 6, what is the hybridization in xenon? sp3d2. What's the geometry of this compound? We say it is octahedral. But what is the shape of the compound, which is molecular geometry? For the shape, we are going to say number of bond pairs first. Bond pairs, how many? 4, right there. The number of lone pairs, 6 minus 4, that gives us 2. So what would we call the shape now? 4:2 on this board. Yes, right there. We say it is square planar. So square planar is our answer for that. And let me quickly go through this. Hydrogen fluoride. The central atom here is fluorine. It's bigger than hydrogen. So fluorine has 7 electrons around itself plus hydrogens, univalents, just 1, making 8, divide 2, that gives us 4. So what is the hybridization in fluorine here? We say it is sp3. What's the geometry of HF? Yes, it is tetrahedral. But what's the shape? Now to get the shape of HF, number of bond pairs, that's 1. You know, there's only 1 atom attached to the central atom. Unlike here where you have 4 attached to the central atom, and we said number of bond pairs is 4. So in this case, number of bond pairs will be 1. And that means the number of lone pairs will be 4 minus 1, and that is 3. If you check your table, you see the 1 bond pair, 3 lone pair case, that the shape that results is linear. So yes, hydrogen fluoride is a linear molecule. So you may want to try other examples. Take as assignment, try IF7 and see whether it gives you pentagonal bipyramidal. Try ICl5. Try TeCl5 minus, this tellurium, same group as oxygen, and then you could try, let's say, BH3. Then I'd like to tell you that there's an exception to this whole thing. You know, I gave you a formula for calculating number of electron pairs. This species, SO3 minus. SO3 minus is an exception because if you try to use that formula for SO3 minus, you get a funny result. This is 6 and then sorry, SO32 minus. Yeah, SO32 minus. So for SO32 minus, I said it's an exception. It's an exception to this whole thing because if you apply our formula, you would have 6 plus 0, that's still 6. Then because we have 2 units of negative charge, we'll add 2 to the 6, and that gives us 8. 8 divided by 2 gives us 4. So you expect tetrahedral, but hell no. SO32 minus has a geometry that is described as the same as the sp3d, which is trigonal bipyramidal. We said the solve for this sp3d hybridized, so it's a special case. It doesn't obey this law, as it were. So that's it for hybridization, and I'm hoping that for small simple molecules you'd be able to tell what kind of hybridization the central atom has, what the geometry of the entire compound is, and then very importantly what the bond pair lone pair ratio is, so that leads you to the shape of the molecule. I'll see us in the next video. Thanks for watching.